Good afternoon. Today we're going to go through our section 3.3 notes, but before we get started you will need a few things. You're going to need to have your textbooks, and you should open up to page 170. You will need your notes that I gave you in class on Friday, and then I also gave you an extra notes packet, and I called them extra notes, but it's really just a reference guide for some of the vocabulary words that I'll be using today that we might need to have a few refreshers on before we get started. You might want to have a calculator. You won't need a ruler today, and you will also need your pens and pencils to take notes. So in the last couple of sections, sections 1 and 2, we've been talking about linear functions. And linear functions are functions that make a graph of a line when we put them on graph paper. We're not so worried about their equations today, but we are going to be worried about the shape of their graph. And when we're talking about lines, they're always going to look like a straight line, but they might have a different slope, which means they rise faster than they run, or they might have different directions. They might be horizontal, they might be linear, they might have a positive slope or a negative slope. We'll talk about those later, but that's what we're worried about today. If you have your books open to page 170, you'll see the term rate of change. And a rate of change is a ratio that describes, on average, how much one quantity changes with respect to another quantity. And that's a lot of vocabulary in there, but we're mostly worried about rate of change is how fast our line is changing. If you look on page 171, if you look on Real World Example 2, they give you a graph. Now, each chunk of that graph does make a line segment, but overall the graph is not a line. But we're going to say, on average, how much does that whole thing change? So if we were to draw in a line from the beginning point to the end point, what's my average slope or rate of change? Remember that we're talking about rate of change, which is a ratio, and a ratio, we have decided, is a comparison of two quantities by division. And we've learned about slope before. We call slope m in algebra, and we've decided that it's rise over run. So what you're doing is you're comparing rise to run. Let's write down our definition first. We're going to say a rate of change is a ratio that describes on average how much one quantity changes with respect to a change in another quantity. Now, one thing to keep in mind while we're doing these videos is that I might write faster than you, and I'm not stopping to ask you questions. So if you need to pause the video so that you can finish writing down the notes, I would suggest doing that so you don't get lost. So we're talking about our two quantities here, and we're talking about rise in comparison to run. Now when we talk about rise on our graph, the axis that goes up and down is our y-axis. So they're really comparing y to the run, which is our horizontal axis, which is x. So we're comparing rise to run and y to x. And we're going to put that down. We're going to say rise over run, and this line still means division. We're talking about a ratio here, but we're not going to actually show the division on our graph. We're just going to show the slope. So this is a ratio, or we're going to say delta y, and remember delta means change in mass. So when you're rising or falling, you're changing your y value over delta x. So we have the change in y up and down in comparison to the change in x, which is left and right. So we're going to talk about up and down in comparison to left or right. If x is the independent variable and y is the dependent variable, then the rate of change is the change or delta in y in comparison to change or delta in x. Delta means change. You might want to highlight that. Okay. Given the following table, find the rate of change. So we have number of computer games and total cost in dollars. We called the number of computer games X and total cost Y. That makes sense because independent variable is something that nothing else controls, whereas Y depends on X. The total cost when you go to a store to buy video games is going to depend on how many games you buy. So that's why number of computer games is X and total cost is Y. So let's look here. If I go from 2 to 4, how much is it changing? It's changing plus 2. How about from 4 to 6? It should be plus 2 again. Now let's take a look at the other side. If I go from 78 to 56, how much is changing? It should be 78. So plus 78. Now if I go from 156 to 234, how much is it changing? It should be 78 again. So do you see how over here it changes at the same rate and over here it changes at the same rate? So if I'm talking about the rate of change, I'm going to say that the rate of change is the change in y, which is 78, over the change in x, which is 2. Now, 78 over 2 is just a fraction that I can simplify. If I take 78 divided by 2, I get 39. I'm going to say 39 over 1 for right now because I know that I'm going up 39 on my graph, but I still have to remember to run 1 on the x-axis so that I show that it's changing as x changes 2. All right. So that table on the previous page showed us a constant rate of change. That means that every video game that I bought, I added $78 to the price. So it didn't matter if I bought 1 video game or 16 video games, each one added a cost of $78. That's not always true, like we talked about on page 171. Take a look at that for now. We're on real world example number 2. We're talking about amusement parks, and the graph shows the number of people who visited the United States theme parks in recent years. The first thing we're going to do is part A, and our textbook says to find the rates of change from the year 2000 to 2002 and from the years 2002 to 2004. So we're going to start with 2000 to 2002, and I'm going to just write down the number as going to be my y, because if I look at the graph, the attendance in millions, the up and down one, is my y-axis, and the year is my x-axis. So we're going to say delta y over delta x equals. Now take a look at the year 2002. The graph shows us that 324 million people visited in the year 2002. So we're going to say 324. And then we're going to subtract the number of people that visited in the year 2000. And on our graph it says 317. Over, now delta x is just our years, and we started with the year 2002, and we're going to subtract the year 2000, and I get, when I subtract 324 minus 317, I should get 7 over 2002 minus 2000 is just 2, or 3.5. That's my slope for the points between the year 2000 and the year 2002. Now let's talk about the years 2002 to 2004. Delta y over delta x equals, now take a look at your graph. In the year 2004, 325 million people visited. Minus, now the number of people in 2002 is 324 million. Over, now I'm dealing with my years. I started with the year 2004, subtract the year 2002, and I should just get 1 over 2, or 0.5. But remember, when we were looking at those graphs, in between each of those points, we saw line segments. So it is linear, but the slope changes between each of the set of years that they're talking about. We can see the difference here. We see that from 2000 to 2002, it increased by 3.5 million. But from 2002 to 2004, only by 0.5 million. So that's part B in the real world example. We just talked about that. And then how many different rates of change are shown in the graph? And we see 3 different rates of change, from 317 to 324, and then from 324 to 325, and then 325 to 335. It changes. Okay, so when the rate of change is the same between any points on the graph of the function, it is called constant. So if I were to draw in a graph, and I have a line, I should label my axes, huh? I have a line. Now, do you see how it doesn't matter if I'm talking about from here to here, from here to here, from here to here? The line is going up and moving to the right at the same rate anywhere on that line. So it's constantly changing. Whereas we had an example in our textbook that looked more like this. It went like this, and this, and this, and this, maybe like that. So these do make line segments, but it's not constant because from here to here's slope is different than from here to here's slope. So we're going to write under here, we're going to say constant, not constant. Linear functions have a constant rate of change. That's something you need to keep in mind today. So now we're going to turn to page 272 in our textbooks, and we're on page 2 of our notes. We're told that we should determine if the following function is linear. And instead of giving us an actual function, they just gave us the table of function values. We know how to find that. That's what we did in section 3.2. We went through and we had f of x, and we picked random values for x, and then we plugged them into the function to find out what our y values were. They already did that for us. So let's talk about this one. If it's constant all the way from 1 down to 13 and from 6 down to, or negative 6 down to negative 14, then yes, it is a linear function. If it's not, then we know that our slope changes from in between different sets of points, and it's not a constant rate of change, and thus it's not a function. So from 1 to 4, I get plus 3. From 4 to 7, I get plus 3. 7 to 10 is also plus 3, and so is 10 to 13. So the x, they work. They're constant. It's always plus 3. Now let's go take a look at the other side. We have negative 6 to negative 8, which is minus 2. Negative 8 to negative 10 is minus 2. Negative 10 to negative 12 is minus 2. And negative 12 to negative 14 is minus 2. So these also work out for us. Yes, this is a linear function because my x values have a constant rate of change, and so do my y values. It doesn't change in between different coordinates. Now if they ask me to write the rate of change, I would write the change in y over the change in x, and I know between each y value I change by negative 2. And between each x value, I change by positive 3. So my slope, or rate of change for this function, is negative 2/3. We're not graphing today. But if we were to graph this, our slope is negative 2/3, so I would fall 2, run 3. Fall 2, run 3. Okay, let's go take a look at the next one. If I go from negative 3 to negative 1, I have plus 2. From negative 1 to positive 1 is plus 2. 1 to 3 is plus 2. 3 to 5 is plus 2. So the x side works out for us again. Now let's go take a look at the y side. I have 10 to 12 is plus 2. 12 to 16, however, is plus 4. So automatically, these don't match up. This side does not work, and this is not a linear function. Okay, now we're going to start talking about slope specifically. And we've already said that rate of change on a graph is the same thing as slope. The difference is the slope we're going to be talking about today is for our linear functions that aren't broken up into chunks with different rates of change. We're only worried about the slope for graphs that have a constant rate of change. So a slope is a, are you on page 172? Go down and look at the find slope part. The slope of a non-vertical line is the ratio of the change in the y-coordinates, also known as the rise, to the change in the x-coordinates, also known as the run, as you move from one point to another. Now, we're going to write that in there, but we're going to worry about the non-vertical line part a little later when we start showing you what the graph looks like. So, we're going to say the ratio, which we know is the comparison of delta y over delta x of the change in the y-coordinate which is the rise, to the change in the x-coordinate, or the run, as you move from one point to another. Okay, we've already talked about this. Slope can also be used to describe rate of change. We know this. It describes how steep a line is. The greater the absolute value of the slope, the steeper the line is. What they're saying is, if I have these two graphs, these might be kind of tiny. And I have this slope versus this slope. This one is steeper than this one. We call slope m and write it as m equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Now the x's and y's are from coordinates or ordered pairs from our graph. They might also just give you the ordered pairs. We know that ordered pairs are written as x comma y. And when we have two of them, we have to label them so we know which one comes first. So if I have the first ordered pair and I write it's x sub 1 comma y sub 1, it's just saying my first ordered pair has the first x and the first y. And then if I have my second ordered pair, I write it as x sub 2, y sub 2, and that means the second x and the second y are found in that second point. So when I start finding slope, I'm worried about change in y over change in x. So I take the two y's and I put them in the numerator. I put y2 minus y1. Then in the numerator, the denominator, I put x sub 2 minus x sub 1. The biggest thing to keep in mind is that if you list y sub 2 first, then you have to list x sub 2 first. Otherwise, you will end up with the wrong slope because you're comparing the wrong numbers. So we can also talk about, we called them delta y over delta x or rise over run. All of these three things mean the same thing. They're just different ways of saying it. Okay, so if we have this example, I'm going to scoot my paper up just a little bit. It says, find the slope between the points -1, 3, and 2, -2. I'm going to list this point as my first point, and this one as my second. And I'm going to say this is x sub 1, comma, y sub 1. This is x sub 2, comma, y sub 2. So to find the slope, I will say m equals y sub 2 is -2 minus y sub 1, which is 3, over x sub 2, I have to list x sub 2 first because I listed y sub 2 first, 2 minus x sub 1, which is -1. Now when you're subtracting a negative, you should write it as 2 minus and in parentheses -1. Equals, now -2 minus 3 should give me -5 over 2 minus a -1 is the same thing as plus a +1. So I get 2 plus 1, which is 3. My slope is -5/3. And I'm going to just leave it in fraction form because when I go to graph, I don't want to say, okay, I need to deal with a slope of 2.68. That's just confusing. Whereas I can say, okay, I need to fall 5, run 3. That's a lot easier to deal with on graph. All right, let's turn the page. We're on page 3 of our notes. The slope of a line can be positive, negative, 0, or undefined. There are 4 different kinds, and if you flip to the next page, I list those for you. We're going to draw these into the graph so you have an idea of what they look like, but for right now we're just going to talk about them. If we have a line that is horizontal, let's draw that in. We have a graph. And we know horizontal is one that goes just left and right. It never touches the x-axis. Do you notice how it's not rising? So our rise is 0, but it runs the whole time. And so we could either say it runs 1, it runs 100, it runs 25. We could say it runs whatever it wants. But we're going to just say it runs 1 for right now. So come down here. It says it will look like this. The rise is 0 and the run is 1. We know that 0 divided by 1 is just 0. So the slope of all horizontal lines is 0. Now, if we have a vertical line, something else happens. Let's draw that graph in. We have our y-axis, x-axis. Here's our origin. If I draw that line in, we know it goes up and down, right? And it's rising the whole time, but it never runs. So my rise, just like I said up here, I'm just going to say it's 1. And my run, it never runs, is 0. So when I come down here and I write my ratio, I say my rise is 1 and my run is 0. But we can't divide by 0, so it's called undefined. In your homework, when this happens, you can write undefined or you can just put UND. That's it. That will work for me. That's fine. Okay? Otherwise, we do like we did before, and we can find out if we have a positive slope or a negative slope. On that previous example, we had a negative slope, and we're going to see what that looks like in the graph here pretty soon. So take a look at this example on page 3. It gives us the coordinates -2, 0 and 1, 5. I'm going to label the first one my first point and the second one my second point, which means that I have x sub 1, comma, y sub 1. And x sub 2, comma, y sub 2. And m equals y sub 2, which is 5, minus y sub 1, which is 0, over x sub 2, which is 1, minus x sub 1, which is negative 2. Now remember, when you subtract a negative, it's the same thing as adding a positive. And I get 5 minus 0 is 5, 1 plus 2 is 3. So I get a positive 5/3, and I will leave it as a fraction. If you were to get like 6 over 3, then you could reduce it to 2 over 1 or 2. Either one of those is fine. I just don't want to see decimals. If it can be reduced or made into a whole number, that's fine, but don't write it as a decimal. All right. I'm going to give you a chance. I'm going to pause for like 30 seconds here. I want you to go through and do B, C, and D. I'm only going to give you 30 seconds, so if you need longer than that, pause the video, finish them, and then we'll walk through them. Okay, let's take a look. So I have these 2 points. I'm going to start with the second one as my second point, and the first one as my first point. And I'm not going to label x1, x2, y1, y2. We've done that before. We know what we're doing. So for the first one, slope equals -3 minus 4, y2 minus y1, over 2 minus a -3, x2 minus x1. Remember that this is actually plus a positive. So -3 minus 4 is -7, over 2 plus 3 is 5. 7 and 5 can't be simplified anymore. -7/5 is my final answer. Okay, let's take a look at the second one. This is my first point, my second point. I have m equals -1 minus a -1 over, now these were the same. I'm still going to list my x2 first. I'm going to say 2 minus a -3 equals, now if you're subtracting a negative, it's the same thing as adding a positive. That happens in both the numerator and the denominator in this case. So -1 plus 1 is 0, over 2 plus 3 is 5. Now take a peek back at the page before this. Remember when we had 0 over a number, we got 0, which is just a horizontal line. So 0 divided by 5 is just 0, which makes a horizontal line. Okay, let's take a look at that last example. We have our first point, second point. I get -4 minus 2 over 5 minus 5. -4 minus 2 gives me -6 over, and 5 minus 5 gives me 0. Go back to the previous page again. When we got a number over 0, which was our vertical line, we can't divide by 0. So it is a line, but its slope is undefined. So we won't write 0, we will just write, hold on one second. Here, we're not going to say -6 divided by 0 is 0, because that's not true. We're going to say cannot divide by 0, so the slope is undefined. All right. So in summary, we decided that there were 4 different kinds of slopes. We have a positive slope, a negative slope, slope of 0, and an undefined slope. So on a positive slope, what that means is when I increase on my x-axis, so as I move from left to right, I also increase on my y-axis. So my slope goes up from left to right. For a negative slope, the opposite happens. As I move from left to right, my y values come down. Looks like something like this. Okay? Now a slope of 0, we decided, is something that doesn't rise, but it runs constantly. So it is a horizontal line. And an undefined slope is something that rises constantly but has no run. So it is a vertical line. All right, turn to the back side of the last page of your notes. We're going to talk about how we're going to work backwards. In the previous examples, they gave us the ordered pairs for both coordinates and said find the slope. This time, they're gonna give us the slope and one ordered pair and tell us to find the missing value. So in our example, they give us a slope of 1/3, they give us the ordered pair 1, 4, and the ordered pair -5, r. R is the missing value. Okay, I'm going to list my ordered pairs. I say I have 1, 4, and -5r. I'm going to let 1, 4 be my first point, and -5r be my second point. I know that if I go to set up my slope, I can say m equals y2, which is r, minus y1, which is 4, all over x2, -5, minus x1, which is 1. Now, I'm going to simplify that. I'm going to say this is the same thing as r minus 4 over -6. I know that if I had a value for r, I could simplify this again and I would find my slope. But we can't do that because r and 4 are not like terms. But I know what my slope is. I'm going to say this is 1/3. They tell me that up here in the directions. So now I just have to use algebra that we learned about in chapter 2 and 1 and start solving for r. Now I know that since this is all over -6, I'm going to put this in parentheses and I'm going to deal with the -6 first. This line means division, so to undo the division by -6, I multiply on both sides by -6. Over here they cancel. So I get r minus 4 equals, now I have 1/3 times -6. Now that is the same thing as -6 over 1. So I get r minus 4 equals -6 over 3. 1 times -6 is -6. 3 times 1 is 3. That can be simplified to -2 because -6 divided by 3 is -2. So I get r minus 4 equals -2. The last step here to solve for r is to undo the subtraction of 4. And I do that by adding 4 to both sides. And I get r equals +2. And that is the missing value. That's the end of our notes. You have the video, so if you need to rewatch it and pick up any of the parts of the notes that you might have missed, you can do that. You have the extra set of notes that talks about the different vocabulary we talked about. We talked about difference, we talked about slope. I put more examples of finding slope in there and simplifying them. There's more examples like this in there where you have to find the missing value. I'm trying to think. I think that should be all that you need for your homework. You for sure need to have this done for Monday in class, and you need to have looked at your homework so that when you come in to ask questions, you're asking questions that you weren't able to figure out on your own. You should use your textbooks, use this video, use the notes that we just finished, use your extra notes. You can also go on Khan Academy, and he has a really great lit video for rate of change and slope in his algebra section. I'm not going to link it to the website. Khan Academy, you know how to get there. If you have any questions, send me an email. Otherwise, I will see you tomorrow. Have a good rest of your weekend.